Hello. Hi, everyone. My name is Avery. I'm from Facebook. I'm going to talk about something that's kind of near and dear to us, which is dynamic graph processing on a platform we've been developing for about 1.5 years now, called Apache Giraph. I've been at Facebook for about 2.5 years, working in the general area of computational frameworks. So I worked on things like MapReduce. Our implementation is called Corona, and I've also worked on Apache Giraph. So the motivation for us at Facebook may be different from what you might have for graph processing, although we like to think that a lot of things can be modeled as a graph. So specifically for us, hopefully some of you use Facebook. If you come to Facebook, you would see in your news feed a lot of different content that we might show you, friends' posts, embarrassing pictures from last night, other kind of public content that might show up. And we need a way to provide really great ranking features for what to show you in your newsfeed. And graph analytics can play a large part in that. Similarly, when you use products like graph search, you also need to have great ranking features so that the data we show you is very relevant. The second area is in terms of recommendations. So there are lots of things we could show you at Facebook, and suggest to you, like, hey, these are some pages you might want to like, or here's some groups that might be really interesting for you to join, or some events you might want to go to on the weekend. And of course, people you might know. So graph analytics plays a large part in determining really good features and ranking algorithms for making those suggestions. And the third part of graph processing and why it's important at Facebook is in the area of everyone's favorite old partitioning problems, so graph partitioning and clustering. And they've got lots of different use cases, but if you just think about, for instance, graph partitioning alone, just taking the idea of how you have a whole bunch of vertices and how you just distribute them across a set of machines such that you could, for instance, minimize network traffic based on your access patterns. Or in terms of clustering, try to organically discover communities within the graph, or find just entities that are very similar to one another. And so we've been using Apache Graph. As I mentioned, we've been using it for some time now. We have a blog post about detailing exactly why we picked it versus a couple of other competing technologies. But by and large, it's basically a product that was inspired initially at its onset in about 2011. We actually gave a talk at the Hadoop Summit about 2 years ago, or 3 years ago now. But it runs on top of Hadoop. And even though it was inspired from Google's Pregel, which had a lot of great ideas, we've taken and expanded it in a lot of ways. And one of the things I'll talk about today is dynamic computation, which we think is a really great innovating feature on top of what's already been done. And the idea behind Apache Graph is you think like a vertex. Imagine you're a vertex in the graph. You have edges that point to other vertices. You have some data associated with yourself, and you have an ID. And you have some computation you can do. So we have these epochs where every vertex will do some kind of computation. It'll send messages. And then just prior to the next epoch, those messages will then be delivered to the destination vertices. More computation ensues, and so on and so forth. Let's just go through a quick example to illustrate how this works and why we think it's a useful model. So here we have a very simple graph of 3 nodes. They're strongly connected. Each node has different vertex values, and we want to propagate the maximum vertex value to every vertex in the graph. You can do this just using a very simple algorithm for the point of view of a vertex, which is send your maximum vertex value to your neighbors, and if you haven't received a high vertex value, you figure you have the highest vertex value, and you stop. So in the first superstep, everyone sends their vertex value to their neighbors. Now here, the middle vertex is the only one that receives a higher vertex value, so it says, okay, I need to propagate that to my neighbors. Meanwhile, the other 2 vertices have not, so they just say, I assume I have the highest vertex value, and they're halted for now. That middle vertex passes its maximum vertex value to its neighbors. Now the bottom vertex receives a higher vertex value, says, oh, I need to propagate that to my neighbors. And finally, everyone agrees that 5 is the highest vertex value in this application. Giraph was built with the idea that it would play with Hadoop very nicely. And we want to leverage existing infrastructure out there. I mean, probably almost everyone here has some kind of Hadoop cluster running. And Giraph supports a variety of versions of Hadoop because there's so many versions of Hadoop out there. So even from 20x, which hopefully nobody here is running, all the way to Yarn, which was mentioned today. And in the old versions of Giraph, in the older versions of Hadoop, the way it's launched is as a map-only job. And in terms of the new yarn, you can actually think of it as a yarn application, which is kind of cool. So let's look at why this computational model is important. If you want to implement something like pagerank, how would you do it in MapReduce? It would take lots and lots of code. It would be complicated. It probably would work, but it would be probably also pretty slow. So if we do it inside of something like Giraph, we can actually think of it natively as a graph application in kind of 2 steps. So at the bottom part of the code block, you can see I'm sending a PageRank value to all my neighbors for 30 iterations. And in the top part of the code block, on the next Superstep, I'm going to sum those messages together, the PageRank values for my neighbors. I'm going to calculate a new PageRank value, and then I'm going to send it to my neighbors again for 30 iterations. Here's how our data flow works. So when you want to load the graph into the Giraph platform, what you do is you specify one or more input formats. And our input formats are 2 different types. One is a vertex-based input format, and the other one is the edge-based input format. And you can specify as many of these as you like, which allows you to do kind of powerful pre-processing transformations on your graph before you even get started, but yet avoiding all the MapReduce jobs you have to do to process your data before you can actually do your real graph application. Each of these input formats is basically divided to splits, similar to MapReduce, but contrary to MapReduce, each worker in this case is going to load as many splits as it can. It just reads the data, constructs the edge or vertex, and sends it off to the destination worker. And the destination worker is based on a graph partitioning algorithm. So you can select that to be whatever you want. In practice, a lot of times you just pick random hash based on the vertex ID because it provides a great way of balancing, a great way of balancing number of vertices, but also incurs a lot of network traffic. And there are other ways you can do. If you, for instance, know something about your data set, you can then do range-based partitioning and other things. So once your data is loaded, and you've done some filtering and pre-processing in this stage, now we can start to get into the computation. We have this notion of a master, which is kind of controlling the way the application works, and I'll get into detail a little bit about that later. And it gives you the ability to actually assign partitions to different workers, changing the way your application is structured as the computation proceeds. But everything is done in memory. So after you've loaded the graph, all data is in memory, and now we're going to start to do computation for your application. So whatever your compute function is, you're going to start doing the computation per vertices, send messages across the place, and then master is going to synchronize things, and then do the next round of computation. And finally, when everything's done, when all your data is ready, you've calculated all those logistic regression weights, or whatever you're doing, you can then store the graph back into an output format. And that can be whatever you want. So in our case at Facebook, a lot of our data is Hive tables, so we just dump it back to Hive table. But it could be HBase, it could be sequence files, it could be whatever you like. So I want to talk about pipeline computation today. And this is, I think, something that sets Giraph apart from other frameworks a little bit. It's the idea that we can make very complex applications that we actually need in production by adding a little bit of functionality on the master. So the master understands and has some logic around what the life cycle of the application is going through. So it can change the computation as the application is proceeding. It can change the in and out message types. It can change the combiner for the next Superstep. And it can set and modify the aggregator values. So aggregator values are basically global data that's aggregated for each worker, pre-aggregated on each worker, and then sent to the master and finally aggregated. And so you can have this kind of application where you have several phases, and even parts of a phase, in which the master is going to tell the workers, hey, you're going to do phase 1A now you're going to do phase 1B, now you're going to do phase 2, phase 3, and based on the data and the output that I have for these phases, I can then decide where to go next in my computation. And so for fun, we're going to go through a great use case on one of my favorite algorithms, which is affinity propagation. So I'll just describe briefly what affinity propagation is. It has nothing to do with this talk, really, but it's just fun, and I did it during a hackathon at Facebook. So the idea behind affinity propagation is from these great researchers. It's message passing and clustering via message passing. And basically, you have these points in the graph, and then you have links between them, where the links indicate a similarity between 2 entities. And the cool thing about this algorithm is that, unlike things like k-means, which force you to kind of upfront declare the number of clusters you would like, affinity propagation actually determines this on its own, organically. So it's kind of unpredictable, too, in some sense. So initially, nobody knows who the exemplars are. Oh, so I'm sorry. So the exemplars are actually the way the clusters are determined. So every vertex will point to an exemplar and say, you are my exemplar. And so that exemplar kind of defines the cluster of people pointing to it. And so there's initialization phase, where basically you can say what the similarities are, you can say kind of who's more likely to be an exemplar, and then there's this intermediate phase as your application is proceeding, you kind of this state where exemplar is not sure who other exemplars are, like even if they're an exemplar. But on final convergence, you should have a case in which vertices all point to an exemplar, and the exemplar also believes it's also an exemplar. So the way you can actually implement this algorithm, the way the researchers describe it, is in 3 phases. So the first is the responsibility phase. So responsibility of I for k. So how well suited is k to be the exemplar for I? And then there's availability, which is that given the fact that I know all of i's responsibilities, how appropriate is it for point I to choose point k as an exemplar? And finally, when I know this information for every single vertex in the graph, I can then figure out which one my exemplar should be. And you want to dampen the way you change your responsibility and availability, just because otherwise it can kind of throw a lot of mess into this situation and cause overfitting. So in the responsibility phase, every vertex, and oh, by the way, I want to mention that this actually fits very nicely in Giraph. That's why I also like it. So in the responsibility phase, basically everyone is going to send what they calculate as their responsibility based on the similarity and previous availability to their neighbors. The way you maintain responsibility is via the edge weights. So edge from A to B indicates responsibility of A for B. And so you spend the responsibility in your responsibility message with the sender ID. It says, I sent you this responsibility, but this is the responsibility I think you have for me. OK. And the next phase is availability calculations. So in the availability calculation, we're going to basically sum up those responsibilities we received in the previous iteration. And then we're going to just essentially sum the positive ones. And then we're going to basically subtract the responsibility I got from that particular sender and send it back. So I then say that availability is back to the senders who sent it to me in the first place. And I calculate my own self-availability. And finally, in the updated, I want to update my exemplar. So every vertex has availabilities for all its destinations. It also knows the responsibilities it calculated earlier for all its vertices. And I just need to take the max of the sum of the availabilities and the responsibilities. And that's my exemplar. But before I can do that, I have to dampen my availability because it couldn't be dampened in ahead of time because I only have availability locally as a part of my vertex value. So everyone's just doing local computation here. There's no message passing, actually. And I've got my new exemplars. So here's what the master logic looks like. Basically, the master is coordinating this whole orchestra. First of all, it's going to say, let's calculate responsibility. Then let's calculate availability. And now let's update exemplars. And now I'm going to have some aggregators, which are kind of our global state, to count the number of exemplars that also think they're exemplars, and to also calculate the number of exemplars that have changed during this process. And so I can have some halting conditions, and I say, well, if the change is small, and most exemplars think that they're also exemplars, then I can stop. And this is pretty cool. So I've already implemented a pretty complex graph partitioning algorithm with Apache Graph. You can also augment it and do other fun things. Like you could imagine, well, affinity propagation does have this one limitation where clusters have to be connected to a hub. So everyone has to be kind of 1 degree away from the hub. Now, what if I want to actually provide clustering that goes deeper than that? So you could think of adding a hierarchical mode where perhaps I collapse those clusters together into vertices and then run affinity propagation over and over again. So that we can do all with master logic. And that's what the power of the pipeline computation brings. OK. So besides having a super powerful model and being really useful in terms of building these really great applications, Apache Graph provides really good performance, mainly because of the fact that it's all in memory, but also because we customize data structures very heavily towards graph processing and towards the types of primitives that you're actually using. So in comparison to Hive, which is what we sadly used to do for graph processing early on before we had Apache Giraph, we can run pagerank and a lot faster. So pagerank you could think of as the application I described earlier. It's basically going to have 400 billion edges. And in this case, we saw a 26x speed up in terms of CPU efficiency. But in terms of elapsed time, which is what users actually see, we saw more than 100x gain. And we have the second application, which is not even really an iterative application. It kind of just shows you, I guess, the power of the platform and why it's just generally more efficient than Hadoop, is a friends of friends score. So anytime you have these kind of common neighbors between people in the graph, you can calculate an affinity for those neighbors, which is a huge, huge calculation. But it's not an iterative one. It's just a one-time pass. And even in this case, we can see that you get huge speed-ups. And this is mainly because Apache Giraph is just way more efficient than our Hadoop implementation. In terms of scalability, we haven't really seen any limits to what we can do but we also haven't had that many, enough machines maybe to test it with. But what we can say, at least, is that when we ran PageRank with 200 billion edges, anywhere between 50 to 300 workers, we saw a linear speed up in terms of the elapsed time. And that's what you would hope to see from any scalable processing platform. On the right graph, what we have is 50 workers. We're still running PageRank from 1 billion edges to 200 billion edges. And we can see that, as you would expect, when problem size goes up, time goes also up. So we also thought it'd be useful to run a benchmark at the Trojan edge scale. And we actually presented these results at a couple of venues last year. But basically, last year we could do this in about 4 minutes in iteration. So we thought that was pretty good. And actually, that's something that I don't think anyone else has really tried before. And just yesterday, we decided to try it again, just to see how far we've come. And we saw that we got about a quarter faster. So now we can do it in 3 minutes in iteration for PageRank. And I just want to mention, this is not it's not a simulated benchmark. This is actually real social edges in the graph. We took a bunch of things like friendships, following, other edges that people in Facebook have, and that's how we constructed this graph. So it's based on actual graph access patterns and not something that we just randomly generated. So the improvements here, what we think about better is because we upgraded to 94. 94 is much faster and awesome. Everyone should do it if you're not doing it already. And the other thing we did was we tuned our GC a lot. We played with the G1 collector, and we found some inefficiencies there in the way we're doing things. Great. OK, so I want to talk a little about graph partitioning, because that's a fun problem as well. So why is graph partitioning important, and why balanced partitioning in particular? So random partitioning is an easy way, a super easy way of distributing data across a set of machines. And it provides a really great balance. But one of the big problems is the fact that you ignore the entity affinity. So here, I've got these 4 machines. I've got these 12 data points. I've divided them equally across all the machines. But say if I have to do a friends calculation from every user, that's going to span out network traffic. Oh, nice. Sorry about that. Oh, that's unfortunate. Give me a second. And so, sorry. This is something that we want to avoid, right? Now, after we applied our balanced partitioning, we want to end up with something like this, where you're minimizing the access patterns across machines while still maintaining that same balance. Because we tend to have these homogeneous machines that we're deploying this data on. We don't want to have hotspots. One has a lot of machines, and one has very big machines, and some have small machines. But being able to deploy in a balanced manner, but still minimizing the access pattern traffic. And so in some examples, one of our cache hit rates grew from 70% to 85%. But more importantly, perhaps, is that the network bandwidth was cut in half, which is a huge savings in infrastructure costs. Just diving a little bit deeper into balanced over propagation, in case you're interested. It's based on our work is actually based on a paper from a couple of researchers from Facebook who published in Wisdom. There are 2 different graphs I want to share with you. So one is the graph on the left, which is explaining the edge locality depending on your initialization and the iteration you're on. So we have a random initialization, which means I assign every vertex to a random partition up front. That maxes out at 140 iterations around there and about 60-something% locality. Now, if we start with your geographical location, we actually can get way, way better locality even without doing much, really. But if we can run this application some more, we can then get to like 77% here, which is really good. Provides huge benefits in the application. And so the graph on the right is an example of a halting condition you might have for a graph partitioning application, which is like the number of vertices that are relocated from one partition to the next. And so over time, what you would expect, or what you would hope for if your application is converging, is that that number would get smaller and smaller over time. And so we see that in both cases here. I want to also share some ways in this improves performance in Giraph itself. You can think of Giraph as kind of like this self-optimizing compiler, if you will. So we're generating graph partitioning algorithms, and we're using that partitioning then to run our applications later on. So for instance, in this example of a 345 billion edge PageRank, we have a random partitioning, which is going to be done in about 160 seconds per iteration. And when we have 47% edge locality, we can get it down to 70 seconds or something like that, which is 56% faster, pretty significant if you have lots and lots of applications you're running with this partitioning. And we're getting very close to actually pushing this as a native feature inside of Graph itself. So the way it will work inside of Graph is you provide us a mapping of vertex ID to a partition number. And internally, then Graph will take that information, partition the graph as you like, and also do all the vertex ID remapping that you need in order to maintain the same semantics that you had before. And some of the interesting problems will come up when you're trying Apache Graph, and you get really excited about graph applications. So you're like, oh, I want to do this thing, and I want to send a message to my friends and my friends and my friends. And what happens is you just end up with a lot of messages flowing through the system, and it's really problematic in terms of handling that. So we figured out ways to deal with this. One of them is to actually avoid going out of core, because once you start going out of core, it gets really slow. And Graph has an out of core mode, but we don't use it at Facebook. We actually just use another technique, which we call Superstep splitting, which I'll talk about here. So one simple example is, let's do a mutual friends calculation between neighbors. Easy enough, right? So that means I'm going to just do two things. I'm going to send my friends, all of my friends, and then I'm going to intersect that with my friend list. Simple. Now I have the mutual friends for everyone, every neighbor inside of the graph. Okay, easy enough. Let's start doing some math. Easy math, really easy math. So here we have more than 1.2 billion people on Facebook every month as of this year. We have more than 200 average friends, and so let's just say the IDs are 8 by integers, 8 by longs. So sums up to about 394 terabytes, and I have, let's say, 100 gig machines. Capacity planning is pretty generous with us, and that means I'm going to need about 4,000 machines to do this calculation. That doesn't include the space it required to actually load up the graph. So when you go and you ask your manager for that many machines just to do a mutual friends calculation, they look at you like this, right? We don't want to make our managers upset. So what we've done instead is use a technique we call Superstep splitting. Superstep splitting is this idea where you're going to subset your edges on a vertex into sources and destinations. You can divide them into any number of groups of sources, any number of groups of destinations. And then you're going to just mix and match, basically produce all combinations of these groups until you're done with the computation you want to do. And this doesn't work for all computations, but it does work well for mutual friends. It works well for a lot of other things like pagerank and other things like that. So in this case, in this case, what we've done is, in the example I've given here, I've just basically done a very simple split, because otherwise it gets complicated. But I say my sources are going to be divided into groups A and B, and then my destinations will be divided into groups A and B as well. And so I turn A on, B off, A on, B off, and then I start flipping things around. And that's when that activation is on, that's when I do this message send and message receive. When it's not on, I don't do anything. And so by using this technique, you can then limit the amount of data that's sent per message per superstep, and be able to handle that mutual friends calculation on a much smaller set of machines, just 200 actually, as opposed to 4,000. Now, right now, this is a manual process. We have this kind of like baked into our computations, and we have some smarts in the master to know exactly how many iterations to run. But in the future, there's no reason why this can't be automatic. In fact, we just have this computation. You can specify up front, like, how many iterations of this do you really want to run? Do you want to divide across? And then, the computation just goes. And so we're working on making that more automatic in the future. Okay. So I just want to share a couple of stats about Graph in production at Facebook. We've been in production for over a year and a half now. I've been very happy with it. We can maintain it with a very, very small team. And we are doing more than 100 Graph applications a week. Sometimes during some weeks, it can be up to 1,000. And our internal repository, which is not just built by our own team, but built by a lot of internal customers as well, has grown to more than 30 applications. People are very creative at our company, and they think of lots of ways they can use the platform across graph partitioning, graph applications, features, machine learning even. And the trailing edge number I didn't throw up just for posterity's sake. We actually are getting very close to that scale, and as Facebook continues to grow in terms of its base of people coming to the site, and as we collect more and more data, and we start getting fancier about the things we're doing, we're going to have to get to bigger sizes. And so our production jobs already can get to the scale of 700 billion edges that we run. So we'll have to keep working on ways to scale it even further. And here I'm going to do a demo of a really cool project that an intern worked on during the summer, assuming this works. So there's no internet, but I've cache the page. That's not necessary. And so what we have here is looking at a graph job. And in this case, what we've done is we actually took Hive queries and we replaced some of them with graph jobs. It's a lot faster, actually, to be honest. So here's a job that's run with 200 workers. We have a couple input tables and input edge formats. And you can see it's ran for 42 supersteps. This is over an hour of running time. There's some GC pauses. As most of you people know who work in Java, GC is like the killer of all your applications. So we keep a lot of stats on it. We have duration of supersteps, GC pauses related to it. We know the problematic workers. We understand GC throughput rates. And finally, if you go down to the timeline, you can actually see, for each of the different supersteps, what's happening. So if I look at superstep 0, I can see when the compute was done for each of these different workers. I can see the final messaging done before the aggregation, how this time varies across workers, which is really important because since we have a parallel application, we need to make sure that all the workers are kind of running at the same speed. And I can do this for each of the different supersteps that's there. Also, I have information, was that going to work? Yep. Available for how my data was loaded. So I loaded this many edges at this time, this many vertices at this time. And this is a great tool for us internally to understand the characteristics of our application, where there are problems occurring, and how we make fixes. Okay. Great. Also, there's a lot of cool related projects people have built. So the great thing about being open source and working with Apache Graph is that people do cool stuff on top of what you've already done. And so there's a project out of Telefonica called graphos.ml, where they've done really neat machine learning libraries on top of Graph, which has a whole bunch of different collaborative filtering techniques, I think other machine learning methods as well. They've tried some ideas around real-time Graph, which is something really interesting to us, and built a lot of tools that are also quite novel, I think. And on the right side, there's something called Graph, which has just been submitted to the Jira page on Graph, which is a distributed Graph debugger. It's pretty cool. So what it does is you can actually take the state of a vertex as it changes over a whole series of computational phases and understand what messages were sent to it, what the changes to the vertex value were. So you can actually debug these super complex programs when you're running at the scale of billions or whatever of edges and billions of nodes. It really gets kind of hairy in terms of understanding what your application is doing. So this is a really great tool. Here's our roadmap. So we don't release very often, apparently, and like once a year, it looks like. And this one is projected for this month. The reason why we don't release often, I want to just comment on that, because Facebook actually uses Trunk in production. I know that sounds scary to everyone here. But we actually have a pretty good code base. It's well tested. We have also internal testing suites. And we want to make sure that everything that we do with this project is pushed back into open source, and that everyone can gain from those things as well. And also, it helps us to kind of maintain, to take advantage of all the great work that people in the community are doing to put into Graph itself. So again, we don't put a huge stock in terms of releases. We just kind of use what's out in Trunk. We create an internal branch. We then compile against our applications, and we launch it in production with some testing before we put it into production, of course. So in terms of future work, there's still lots and lots of things we can do. The first thing that's kind of top of mind right now is that with so many applications and some of them taking hours to run, we want to find a way to schedule these nicer. So we have some long-running applications, we have some short-running applications, but we don't want those long-running applications to kind of hold up the cluster for long periods of time. And so what we're going to work on is something called automated checkpointing, which means that after some period of time, your application is going to basically save its state to disk, and then it's going to stop itself, go to the back of the queue, and when it restarts, it'll just resume from the point at which it was before. This adds a little bit of fairness to the scheduling policy we have. Another thing we want to do is, we've been continuing to do actually, is really investigate alternative computing models. There's been some terrific research done from a couple different places on how we can improve Graph. One of those patches, actually Graph++, is up for code review. Both of these are really around relaxing the BSP model, the bulk stream as parallel model that Graph uses. This idea that you have these epoch, computation, then you send messages, then you do on the computation phase, and so on and so forth. But maybe loosening that a little bit to get better performance. And of course, performance is top of mind. So we have a couple of performance things we're testing right now that I think will get a pretty good gain, maybe another 25% gain, but are not quite ready to put up yet. And performance is, of course, important just because we get more and more applications, and we can only get so many more resources. Those machines are expensive. So we're continuing to crank out on that front and work there. But really, what's more important than performance is the two things below, which is one is lowering the barrier to entry. One thing that's awesome about what Hive did for Hadoop was it made it accessible to everyone. So in fact, a lot of people at Facebook don't even know that they're really running Hadoop. They're just like, my Hive query is slow. That's it. And so looking for that kind of equivalent to what Hive for graph processing would be, what's that higher-level construct library that makes it available to a huge portion of the population, is something that we're continuing to investigate actively. But the other thing, of course, is applications. I mean, working on these frameworks is super fun. There's a lot of great problems, but at the end of the day, we need to make impact at Facebook. And so continue to build up our application suite and improve things, and just continue. We already are using a lot of different products, but really to just continue to push on that front is something that's always top of mind for us. And so this is our team. It's a small team, as I mentioned. Everyone here is doing development, writing applications, doing maintenance. We're on call once a week. Not once a week. One a week, and then we rotate. And it's been a lot of fun working with these folks. So with that, I think I'm done, and I'd be happy to answer any questions. Oh, I think, by the way, the moderator or the folks in the back suggested that you please use the microphones if you ask questions. I'm sorry.
That was a really good talk, thank you. I was wondering what your opinion on was how it compares to GraphLab and GraphX.
Okay, great question. So the question is about comparing Giraph to GraphX and GraphLab, both of which are pretty cool, by the way. So GraphLab is a C++ implementation, also kind of vertex-centric, but uses this gas model, right? And it's a little different in terms of the scheduling, because you have to use MPI for it. In terms of the model, it's very different. So they use this gather, apply, scatter model as a way and they use the way of sharding the data across. They don't use a vertex-centric model in some sense. They actually partition the edges across multiple machines. And these are really neat ideas. Also, the thing is asynchronous. Now, when we ran some early experiments with GraphLab versus Giraph, when we started this project, we actually found Giraph to be a bit faster. But that may have changed in the last 2 years. And in terms of usability, for us, it's really hard to leverage something like GraphLab because of the fact that it's C++ and you need to use MPI schedulers for it. The fact that we already had a dupe in place made it just very natural for us to then leverage that operational experience and the ease of use for using Apache Giraph. GraphX, on the other hand, is basically something built on top of Spark and Spark's RDDs. It leverages some of the ideas of GraphLab, and I think it's still pretty early on. I think one important thing to note as a difference, though, is that as far as we've seen, nothing else has been able to scale to the size of the data that we need at Facebook. And so that we're talking about hundreds of billions or trillions of edges. And as far as I know, most of these other projects have been working on the scale of billions of edges. Like a lot of the test sets are available out there, unfortunately, there's two that are used very frequently. One is the Twitter graph, which is like 1.4 billion edges, and then the other one is this Alta Vista web graph, which is only 6.6 billion edges. We need to run something at least 2 orders of magnitude larger than those.
One more question, quick one. Do you have any plans to open source any of these dashboard kind of applications that you have on Giraph?
Oh, like Giraphic Jam? Oh yeah, so we'd love to open source Giraphic Jam. The problem is this. There's no actually easy way to get the information that Giraphic Jam is displaying up there. Actually, we do some really nasty things like screen scrape the job tracker UI, which is not really going to be compatible with every single version of Hadoop out there. So we could do it. We could open source it, but it would only, it only works right now against our implementation of Hadoop, which is called Corona. Your mileage would vary.
Thank you.
Yeah, thanks.
So this looks like a very, very sort of big data friendly way of doing things, where if you have to do things on a very large scale, you necessarily have to simplify a lot of things you do, otherwise it doesn't work. So my question was, did you guys, this is a very iterative approach where it's just like a CPU, the clock cycles every time an iteration happens throughout your graph. Have you guys given any thought to maybe a data flow type approach rather than an iterative approach, where you would treat your graph as a bunch of producers and consumers of data, and then they would allow them to communicate, and this thing would function kind of like a neural network?
Yeah, so there is a lot of work on, I think, if you understand your question correctly, it's more of an asynchronous processing model where vertices kind of operate as independent compute units. They can send messages, they can receive them, process them at their leisure, and you have a scheduler that then kind of figures out what's the best vertex to process at this particular time. And there's a lot of research work on that. GraphLab is one example, for instance, but there's others as well. I think there was a project out of Cornell called Grace that did something similar. The problem with that is it gets very complicated. So you can do it, but for instance, you might have a problem where message queues are blowing up for one particular vertex and then you run out of memory. How do you make sure you throttle these things? And the other part is about the fault tolerance aspect and the repeatability. So at this point, when you've gone asynchronous, you kind of don't know, like, will this algorithm converge? Probably it will. Maybe it will. I don't know. And also debugging becomes very challenging. Like, was this I mean, I can't repeat the exact same case again because I don't know exactly what's happening in the system. So it adds a lot of complexity, and there are big potential wins you can get in terms of better utilization of resources, maybe better networking, better CPU. You don't have to worry about the balance and imbalance that we have. But for now, we've been playing with the idea a little bit and trying out some prototypes, but it's a little bit tough to productionize at scale, huge scale.
And the other thing, did you guys look into the equivalent of, say, query rewrite and query optimization for this graph database?
Query optimization. No, we haven't done any like we haven't done any kind of like historical now. No, we haven't done that stuff yet. Right now, Giraph is very low level, so you're actually telling the system what you want it to do. In order to do some kind of optimization, we have to have some higher level APIs and have to understand some data about which implementation would be better for you. We haven't done that this time.
Thank you.
So earlier you said something about dynamic graphs. So can you say something about that?
So with respect to dynamic graph processing, I was referring mainly to the fact that we can change the application as it's running. So being able to inject have the logic which is available to change processing, change the computational flow, the message types on the fly, if you will. And not really, so we may not actually understand exactly what the application would do ahead of time without understanding what the data is itself. But in terms of dynamic graphs, Apache Giraph is also kind of, I think, more unique in the sense that we allow you to mutate the graph as it's running. So you can add vertices, you can delete vertices, you can add edges, remove edges as the graph is being processed. And some frameworks are limiting in that fact.
So you mentioned the master node has some special responsibility. So do you have to handle the resources for master node, differently than the workers?
So with respect to what the master node is doing, it's just actually has very little responsibilities. All it's doing is it maintains a zookeeper server, which is kind of keeping the state of our processes up. And the other thing it's doing is it's executing that logic. So after every superstep, it's going to get those aggregators, it's going to make a decision about what to do next, and then just basically broadcast information to the workers.
Okay, so one more question. So you said you had to do some tuning in terms of garbage collection and a few other things. Can you talk a little bit about that?
I mean, just similar to anyone who works with the JVM, there's a lot of tuning necessary in order to make your application run as fast as possible. For us, it's a little bit tricky because we have these messages that they're basically garbage. They're generated, they're being sent over the network, they're being processed, and we throw them away. So it's really around, probably for us, is mainly increasing the new size to be very large in most cases, and then making sure we have the right number of threads available for garbage collection and things like that. Any other questions? Thanks.